Hi there! Sometimes people build circuits on PCBs or on perfboards that seem to work fine and then over time stop working without any apparent reason. More often than not, the problem is the way the components are soldered on the board. Soldering components seems daunting to some people, and some other time it seems so easy that it is completely neglected. The truth is, soldering is relatively easy, but requires to follow certain rules to avoid mistakes and to make sure everything is put together in a way that it works and does not break over time. In this video I will give you my take on how to solder, a technique that I have perfected over the long years of my career. Before getting into the video itself, please pause it and take a few seconds to subscribe to the channel if you haven't done so already. Subscribing is free and allows you to be notified when new videos are posted on the channel. Also, please consider helping the channel to grow and become better. You can do so at no cost to you by simply using any of those affiliated links in the video description below to buy either the listed items or to buy anything else you need from Amazon. Just use the link to reach the site and go from there. And if you are more inclined to donate money, you can also do so, either on PayPal as a one-time gift or on Patreon to make a periodic donation. Even $1 single will do. All the links are in the description below. Now let's go back to the subject of today. Let's start this talk by showing you some typical soldering irons. This one has a conic tip and a power of 15 watt and can be plugged in directly in a power outlet. It is a very simple model that doesn't have any special control. Once you plug it in, it starts getting hot and there are no thermocouples to stabilize the heat. This screw here on the side is used to lock in place the tip, which can be replaced with a new one once it becomes too corroded. The corrosion happens during the usage of the iron, and it is caused by the tin and lead of the solder that chemically react with the copper of the tip to form an alloy that sometimes creates also a brittle residue on the tip itself. Cleaning periodically the tip removes the alloy, but also erodes the copper tip a little bit at a time. The heating element of this kind of soldering iron is basically a resistor located inside this tube, which is in contact with the tip to transmit the heat to it. Since there is no thermocouple, the tip gets warmer and warmer until the amount of heat that is transferred to the tip becomes equal to the amount of heat that is dispersed in the air. And this causes this kind of solder to be really unreliable in terms of the temperature it can reach. This other solder has an identical construction, but has a power of 40 watts, which would make it able to reach higher temperatures than the previous one. But since it also has a bigger tip, the temperature remains about in the same range. The difference is that with a higher power it will be able to provide a greater heat to the surface that needs to be soldered, without losing too much temperature in the process. This third iron still works with the same principle, but it has an even bigger power of 60 watts, and of course it has an even bigger tip, which now needs 2 screws to be held in place. This other model works slightly differently. It still uses a resistor to heat up, but this time the resistor is the tip itself. This device has a power of up to 140 watts. The trigger has 2 positions. If you push on it a little bit, you get a power of about 100 watts. If you push it all the way, you get the full power of 140 watts. All this power is used to quickly bring the tip to a temperature high enough to melt the solder. Once you finish soldering the 2 parts together, you just release the trigger so the tip cools down quickly. And in fact, if you were to keep this iron on for a long time, the tip will soon become incandescent and break. This iron is mostly used for quick soldering work, for quick repairs where big components are involved. It is not at all recommended for soldering delicate components on a PCB. And finally, here is also a so-called soldering station, which is the one I use the most. The soldering iron is powered with low voltage in DC, which ensures protection of the components being soldered. The station also allows you to set the temperatures for the tip to the most adequate for the job you are doing. This is made possible because this kind of iron has a thermostat inside that reads the temperature of the tip. And there is even the possibility to tune the reading of the thermostat to make sure that the temperature set on the station is actually the same as the tip on the iron. Tips for this iron come in different shapes, depending on what you need to do. Because of that, it is easy to interchange them just by unscrewing this part and removing the whole covering tube. The tip is inserted directly on top of the heating element, and you can easily remove it and replace it with another one. This kind of tip is of different material than those of the previous solder irons. Those were made of copper, but this one is made of steel. And since the steel doesn't bond very well with the solder, the tip itself is covered with a layer of nickel-chrome alloy. This extra layer allows the solder to stick to the surface of the tip, making the soldering procedure possible. These steel tips are much more durable than the copper tip. When I was essentially using only copper tips in the past, I had to replace them every year, or often, depending on the amount of usage. This steel tip, instead, is on this soldering iron since at least 3 years, and still is in pretty good condition. Here are all the different tips I use with this iron, depending on the job I need to do. This one has a conic shape, this other one resembles a knife, and this last one is shaped like a tapered chisel, and actually is the one that I use the most. This white part of the soldering iron is the heating element, which also contains inside the thermocouple to measure the temperature. The tip is inserted directly on top of it, and then you lock it in place with this covering cylinder screwed at the base close to the handle. This soldering station is also equipped with this nice soldering holder and this sponge that can be used to clean the tip. Here is another kind of holder which is very useful for traditional and more powerful soldering irons. The tip just comes out from the back above the workbench in such a way that doesn't get in touch with anything that lays around. This holder is not that good for very low power irons, like this one, because the tip remains inside the holder and possibly touches the walls, causing the heat to go away and the temperature of the tip itself to lower. For this kind of low-power soldering irons, a better stand is this one, which doesn't even take much space on the bench. All of these are examples of soldering irons working with electricity. There are, however, some portable irons that use butane or propane gas instead of electricity to heat up. The gas is usually contained in a small cartridge inside the handle, and close to the tip there is a catalytic heater that uses the gas to heat up the tip. To solder something, in addition to have a soldering iron, we need of course the solder. The one used for electronics applications is normally sold in spools like this one, and comes in several diameters. Soldering wire used for electronics is quite different than the ones used in other fields like plumbing. First of all, it is thinner, and then it has what is called a rosin core that goes through the whole length of the wire. Rosin is the name of a resin extracted from pine trees, and we'll talk about more of that later. Soldering wires are made essentially of an alloy of tin and lead, in the ratio 60:40. For this one, 2% of the whole volume of the wire is occupied by the rosin core, or simply flux, and the diameter is 1 mm. This other spool has still an alloy of tin and lead in the same ratio 60:40, but has a volume of flux variable between 1.8 and 2.2%. The diameter of this wire is just 0.6 mm, and because of that it is better suited for very small components. This last spool is made with lead-free alloy, made of 0.3% silver, 0.7% copper, and the remaining 99% tin. This wire has a diameter of 1.5 mm and has a 2% rosin core. Handling lead-based soldering wire may leave traces of lead on your fingers, so it is best to wash thoroughly the ends after finishing working with it. Lead-free solders don't have this kind of problem, but they melt at a temperature higher than the lead-based soldiers, and so they are more difficult to handle. Not to mention the fact that certain components cannot be heated too much, so the lead-free option is not always a good one. Lead-free soldiers, in fact, is mostly used in the industry, where other techniques are used to solder components, rather than using a heated soldering iron. From my perspective, I definitively prefer to use the lead-based solder because of the low melting point and easiness to use it. After all, washing hands after use is not such of a big problem, right? And now, since we just talked about melting points, let's spend some more words on that with the help of a diagram. This diagram describes how the melting point of the solder changes when the percentage of tin and lead changes. Let's start by looking at the horizontal axis. On the far left, we basically have pure lead, while on the far right we have pure tin. You can see how the pure lead melts at a temperature of 327 Celsius, while the pure tin melts at a temperature of 232 Celsius. But if we move in between the two extremes where we have a certain percentage of lead and the remaining percentage of tin, the temperature is different, is lower in particular. And with an alloy made of 63% tin and 37% lead, we have what is called the eutectic point, or the point where the melting temperature is the lowest possible. Such temperature is 183 Celsius, or about 361.4 Fahrenheit. Below this temperature, the two metals and any of their alloys can only be at the solid state. At the eutectic point of 183 Celsius, only that particular combination of metals is able to melt. All the other combinations are still solid. At temperatures above the eutectic point, metals start melting in an uneven way, and the partially solid metal is either the lead or the tin, depending on the percentage of materials. For example, with an alloy made 50% of lead and 50% of tin, we would be on the left side of the eutectic point. There, between the temperatures of 183 Celsius and 327 Celsius, we will have some solid lead in molten mix of both lead and tin. On the opposite side, we would have solid tin in the molten mix. And above that blue line, everything is just liquid. Now, why do we care about this? Because we want to be able to solder electronic components at the lowest possible temperature, and so we want to be as close as possible to a mix tin-lead in the ratio of 63:37. And that's why the solder wire for electronics has those percentages of tin and lead, or at least very close to it. So, with this kind of alloy, we just need an iron tip heated at about 190 centigrades, 200 maximum, to make sure that it melts the whole alloy. No need to use higher temperatures, because they will not change the behavior of the alloy. They will only cause the electronic components to be damaged by the excess heat. And that's why we prefer to use soldering stations in a lab, where we can adjust the temperature so that it is enough to melt the solder without damaging the components. As we already mentioned, rosin is a resin extracted from the pine trees. This resin has various uses. Here, for example, is a block of resin used to treat violin strings. Musicians usually name the same resin with the name colophony, directly derived from the name of the ancient Greek city of Colophon, where they mastered the use of the resin for various usages. The rosin is basically colophony treated with a heating process and mixed with a solvent, normally isopropyl alcohol, to make it more fluid. In this form, it is injected in the soldering wire while it is produced to form the so-called rosin core. With different amount of solvent, it is used also in the form of a paste, like this one, or even a liquid, like this other one. Liquid rosin is very useful to solder and desolder SMD components. The paste is used to apply solder to thick wires, where sometimes the rosin core is not enough and more is needed. Personally, I also use the rosin paste to clean the copper tips of soldering irons. Let's see now what happens when we melt a piece of solder. You see, there is a lot of smoke that comes out. Many think that the fume contains particles of the metals composing the solder, the lead in particular, and think that if they breathe it, they will actually take lead in their lungs. Well, that is not really true. The temperature of the soldering iron is not hot enough to cause the lead or the tin to evaporate. The fumes you see are actually produced by the rosin core. It is the rosin that, once heated, first melts and then quickly starts boiling and evaporates. The fumes are mostly made of rosin. Now, breathing rosin is not nice, it doesn't have a very good smell, and in certain people induces a burning sensation in the nostrils. Some people also is allergic to the rosin fumes, and they cause the person to have problems breathing, or not be able to breathe at all. To eliminate or at least reduce this kind of problems, there are devices called fume extractors that are readily available in the market, or you can build one yourself if you like. I built my own. It is basically a container with openings on the front and on the back. Behind the frontal openings there is a carbon filter, and behind the carbon filter there is a fan, in my case an old computer fan, that sucks the fumes in front of it and forces them to go through the carbon filter. The carbon filter removes the rosin particles and the rest of the air comes out from the openings in the back totally clean. Keeping such a device close to the area where you solder will eliminate most of the rosin fumes that are generated during the soldering process, and therefore will prevent you from inhaling them. A classic example of a device that does nothing for the lab itself, but helps you stay healthy while soldering components. Rule number 1 to solder correctly is to have a clean tip of the soldering iron. The tip needs to be clean from the breeze and has to shine with the tin applied to it. Let's clean this tip to show how the clean is supposed to be done. First, we need to power up the iron. It needs to be hot to clean the tip. While we wait for it to reach the correct temperature, let me show you what I use for cleaning. This one is the same rosin paste we already talked about. This one instead is a sort of copper sponge. Copper is very malleable and tender and is very useful in scraping out the debris from the tip of the iron without damaging it. And this is especially important for tips made of steel like this one. In these tips, the tip is covered with an alloy of nickel, so the solder can adhere to it. If we scrape the tip with something hard, even just sandpaper, we would end up removing the layer of nickel, making the tip unusable. The copper sponge is perfect in this case, so basically you use the sponge to remove the debris and the oxide from the tip of the soldering iron. A better way to use this sponge is to have it in a container like this, so you can easily access to it even if you have just one available hand while you are soldering something. If the layer of oxide is very thick and difficult to remove, I normally use the rosin paste like this. I just put the heated tip in the paste for a few seconds to make the rosin dissolve the oxide. Then I remove the tip from the paste and I clean it with a dry cloth or cotton, like this. And as you can see, the tip has become already very shiny. Once all residues are gone, as well as the oxide, you take a piece of solder and melt it directly on the tip of the soldering iron. Then you remove the excess with a copper sponge. Another way to clean the tip is to use a piece of natural sponge soaked in water. The tip can be cleaned directly brushing it on the sponge. Note that when you do this, the temperature of the tip goes down, but after a very short time it goes back to the value where it can melt the solder. Now that we know how to keep clean the tip of the soldering iron, let's see how to use it properly. For this example, I will use this board and a few components. Let's start with these resistors. I will bend the terminals and put them in the holes. Then I will bend them to the outside to prevent the resistor from moving when I put the board upside down. So first I will solder one terminal the way it is not supposed to be done, and then I will do it the right way and will show you the difference in the quality of the soldering. Some people does this. They put the solder on the tip of the iron and then they try to make the solder stick on the terminal and the pad. This, however, is really wrong. We have used all the rosin core on the tip of the soldering iron, and there is no rosin left to remove the oxide from the wire and the board and help the solder to bind with the copper of the pad and to the wire. Over time, this connection will continue to oxidize, and after a while it will fail, making the electric connection unreliable. Let's do it now the right way. First, we touch the pad and the wire at the same time with the tip of the iron. The flat shape of the iron tip will help transfer the heat to the wire and the pad, which will both reach a temperature that will be capable of melting the solder directly. It is at this point that we touch with the solder the area that has been heated, not the soldering iron tip itself. The solder needs to be melted by the parts that need to be soldered together. This way, the rosin will spread on these parts, it will eliminate any residual trace of oxidation, and it will help bind the solder with the metal of the pad and of the wire. Once this is done, we can remove the remaining solder, and at last we can remove the iron tip, thus letting the solder, the pad and the wire to cool down naturally without blowing on it. And now we can compare the two soldered points. You see, the solder point done correctly is shiny, while the one we did it the wrong way is kind of matte and has a brittle aspect. It is what is called a cold soldering, because the pad and the wire were cold when I put the solder on top of them. The solder cooled immediately and crystallized, making the surface look matte. If we look at the other side of the board, at least in those cases where we have a double-side board, you can see how, with the right procedure, the solder spreaded also on the other side. With the wrong procedure, instead, the solder does not spread to the other side, or it spreads unevenly. Let's take a look at an enlargement of those two connections, so we can see up close how they look like. We can see the two solder points side by side now. The one on the right is the wrong one, and the one on the left is the right one. See how dirty the connection looks like on the right, and how clean and shiny the one on the left? The dirtiness of the right connection is mostly due to the oxide still present on the metals, along with other residues that were transferred on the connection by the tip of the solder. The good soldering point is instead clean and shiny because there is no dirt and no oxide. Once we completed the soldering of a component, we just need at this point to remove the excess wires and we are done. So let me show you now again the correct procedure a few more times, so you can appreciate the way it needs to be done. I will solder now the two other resistors that I have prepared. I first bend the terminals, both of them, and I insert the wires in the board holes. You can see how the components are now free to move on the board and how they can fall once I turn the board upside down to solder the parts. To prevent that from happening, once again, I bend the wires a little bit toward the outside so the components cannot fall anymore. And now I can solder everything. Note once again the whole procedure. 1. Touch with the iron tip the parts that need to be soldered. 2. Touch the parts with the solder, which will melt directly on them. 3. Remove the solder wire from the area. 4. Remove the iron tip. The iron tip must be put in there first and must be removed last. Let's try now with this other component, an IC socket. Since I cannot really bend the terminals of the socket, I usually use a piece of tape to hold the socket in place, and then I turn the board upside down to do the soldering. In the case of components with multiple pins, like in this case, I usually solder first a couple of pins at the opposite ends, so the components will not move anymore while I solder the other pins. I can even remove the tape once I solder the first two pins, and then solder all the other pins. And you can see that once you get the handle, soldering becomes a process pretty fast. Now, look what happens if I remove the iron too early. See, the solder wire remained attached along with the rest, and that's why it is important to remove it before removing the soldering iron. Let's do now one last example with this electrolytic capacitor. Same procedure as for the resistors. insert the wires in the holes, take them apart a little bit, then put the board upside down and solder the parts. One last thing, very important. You may have noticed already that I did not put a lot of solder on the connections, just enough to bind them together. Too much solder and I would create bubbles of solder that could touch to each other, especially when the wires are close to each other. Let's now take a look at something different. How do we solder together two pieces of wire? First thing to do is, of course, to remove the insulation from the wires if present. And we also need to insulate the connection once it is done. I will use a piece of shrinking tube for this, which is what I do most of the time in my projects. Actually, if you watched my recent videos on the assembly of the Theremin V2, you must have seen me using this technique several times. Now, since this one I choose is a stranded wire, what I usually do is to push them together from the ends, so they intertwine together across their length. Once that is done, I use the soldering iron to heat the wires, and then I put the solder, which is melted directly by the wires. Then I remove the solder, and finally I remove the iron, exactly the way I explained before. Finally, a piece of shrinking tube inserted over the connection and shrunk with a heat gun makes the connection perfectly isolated. Simple, right? Well, there is something that you need to be careful about. Sometimes, especially if the wires were exposed for some time to the air, their surface could be covered with oxide. If that is the case, it is better to remove the oxide before soldering the two parts together, otherwise the solder might not bond with the wires and the connection could not work over time. This is especially true if there is a lot of oxidation on the wires, because the rosin core will not be enough to remove it. What I do in such cases is to take a piece of sandpaper and use it on the wires to scrape away the most part of the oxidated layer. Only then I go and solder the two parts together. This time, though, since there was oxide, I first tin the two wires separately to make sure that enough rosin goes on the wires and removes any remaining residue. Once the two parts are tinned, I just wrap the two wires to each other and then I solder them together with the same procedure I used earlier. Once the two parts are connected, I use again the shrinking tube to isolate the connection. One last thing I would like to show you is the procedure to desolder a component from a board. This may be needed in those cases where we make a mistake in putting a component or when we need to replace a component because it broke. Let's make this example with the same board I used for showing you how to solder components, and let's say we need to remove the capacitor to replace it because it was damaged. There are different ways to remove a component. I will show you how to do it in a couple of cases, but keep in mind that the ultimate process is to avoid the breakage of the board itself, because too much exposure to heat would cause the pad or even the tracks of a PCB to detach from the board itself. The first technique I want to show you is the one that uses a desoldering wick. It is basically a bunch of thin copper wires braided together and impregnated with rosin. This wick has the property that when heated to the right melting point has an elevated capacity of absorbing the solder from a board. We use it by putting it on top of the solder that we want to remove, and then we heat it with a soldering iron from the top. The heat will propagate through the braid, which will start melting the solder and absorb it. Another tool very useful for removing bigger amount of solder is to use a desoldering pump. There are those that need a soldering iron, and there are those that can melt the solder by themselves, but the main concept is to melt the solder and then suck it out with the pump. After that, pushing on the pump, the solder can be ejected from the pump and thrown away. Sometimes you need to use both, first the desoldering pump to remove the most of the solder, and then the wick to remove the small remaining part. Let me show you now how the procedure works on the component itself. Since there is not much solder on the connections, I will just use the wick. Once the solder is removed, the component should come out easily. If it doesn't, then we just need to grab it and gently pull it while heating the connections with the soldering iron. And this concludes my tutorial on soldering and desoldering basics. I hope this has given you enough information to be able to make good soldering joints on your circuits so they can last a very long time. Please don't forget to give me a thumbs up and to subscribe if you haven't done so already. I will see you in the next video, and in the meantime, happy experiments!